Hey yo, what's crack clacking? It's your boy. Okay. We are going to jump right into this. This looks like a paper two because I can see the calculator sign. And so we're gonna, you know, really get this one done here. So coffee shop owner, uh, average temperature T. So right away I'm getting the linear vibes here. Average temperature T. Also shows a number of coffees n. Now, if we look at our relationship, n represents y, t represents x. In other words, n is our dependent variable, t is our independent one. So this is very important because we're going to be using our calculator to create a list. I'm going to do that one right now. And by creating a list, we can actually get our linear regression data. So if you go to second function list, go to under edit, you press edit. And then you're going to have your L1 column and your L2 column. In your L1 column, you're going to want to put your x values, 16.2. And that's what I'm doing right now. So bear with me. You can skip through the parts where I'm punching in the numbers into my calculator. But if you just want to stick around because you like hearing the sound of my voice, then please listen to me. Do that. So I punched in all my numbers. I am going to go to under calc. Now we're going to press linear regression, ax plus b. By the way, I'm using a TI-84 plus. So we're going to go linreg. X list is L1, y list is L2. Calculate. And what I get, for at least for me here, is my A is equal to negative 9.93. And my B is equal to 222. Boom. Find the value of A and B. We just did that. To the nearest integer, estimate the number of coffees sold when T is equal to 16 degrees Celsius. That just means we're going to plug and chug. So N, we calculated A as being this number here. T is 16, and plus B, 222. And if we do the quick math, that's about 63.12. However, we want the nearest coffee, so that is 63. Find the value of R. R is given in your calculator, and what I get here is 0.955. Alrighty, let's move on to the next one. Cumulative frequency, distance d on the x and number of students on the y. Find the median distance a student travels to get to school. Well, we have 160 students. The median occurs at the middle value, which is 80. So if we line this up, and then we do a little interpolation, as I like to call it, we see that we line up with 3. So our median distance is 3 kilometers. Alrighty. Find the number of students who travel between 2 kilometers and 4 kilometers to get to school. Again, this is just a bit of lining up. So we move from 2, and we line that up with the number of students, which is apparently 30. And we do that for 4 as well. So for 4, we move up, we interpolate. That's the word. Word of the day, interpolate. And then we move to 130. And so the number of students between these two, the lower bound of 2 kilometers and the upper bound of 4 kilometers, is the difference between 30 and 130, which is 100. So indeed, we have 100 students as our answer. Now find the percentage of students who travel more than 4.5 kilometers to get to school. Okay, so 4.5 kilometers is right here. And if we interpolate, we line our stuff up, we find that the benchmark for 4.5 and greater starts from 140. And to get to from 140 to 160 is 20. So 20 out of 160 is our fraction. And we want a percentage, so we multiply by 100%. And so 20 divided by 160 times 100 is 12.5%. And that is our answer. Nice. Let's move on to the next one over here. Alrighty, we have a natural logarithmic function with a bit of transformations. This doesn't seem too bad. Find the x-intercept. Well, of course, if you wanted to find the x-intercept, You could just plug in the function into your calculator and let your calculator do it for you, but that's a waste of time because it's very easy to find these quick intercepts. So we know that the x-intercept occurs when y is 0, so we set the numerator to 0. Now, in order to get any argument for a natural logarithm to be 0, our argument itself has to be 1. So we set the inside arguments to 1, like this. And isolate for x, we get -1. And so our x-intercept occurs at -1, 0. Now our y-intercept similarly is when we plug in x as 0. So f of x is equal to ln 2 over 2. And as a decimal, if I plug this in real quick, ln 2, we get 0.347. So our y-intercept is 0.0347. Kaboom. Now find the equation of the vertical asymptote of the graph of f. Again, you could plug this in, but it's such a waste of time because you just really need to know that if our natural logarithm was originally set here without transformation, the regular vertical asymptote was always 0, and if we shifted it 2 units to the left, then it follows that, well, our vertical asymptote is just -2. So x equals -2. Now, of course, you could do the whole shebang with the limit as x approaches infinity, or as x approaches, well, you can say here, you can say that as the whole shebang with the limit there. You don't need to do that. You're SL. Whatever. Find the area of the region enclosed by the graph of f, the x-axis and the y-axis. This is the enclosed regions right here. We know that the x bound here is 0. So, x equals -2. We know that the bound here is x equals 0. And so it follows that our area is just the integral between these two bounds. Oopsies, I'm not doing it right. Not negative. Oh, sorry, I'm getting this confused. This is not -2, this is -1. It's our x-intercept. I confused it for a vertical asymptote. This is -1 to 0 of our function, this right here. And we're not going to do this ourselves. We're going to get our calculator to do this. So if you go to math and you go to your integral function or your integral operation, you can just plug this really quick. I'm doing that right now. And if you divide by 2, with respect to x, of course, you will get 0.193 units squared. Now we want to make sure we have this even though we don't know what our units are, because IB is a picky thing. And we want to make sure we're making the people at IB happy, whatever that may look like. So, a farmer wants to build a rectangular, optimization. A farmer wants to build a rectangular enclosure for his chickens. The area of the enclosure, boom. The fencing used for AB distinctively is $13. And the fencing for the other 3 sides is distinctively $4 each. Now, what I'm going to do is I'm going to call this x and I'm going to call this y. And based on the information, we know A is x times y, which is just 350. But we also know that the cost is equal to 13x plus 4y plus 4y plus 4x. Okay? And if we consolidate like terms, we get this. Now we have a 2-variable situation, and in math, 2 variables always makes it a bit harder to work with. But we do have one axiom. This axiom can, if we substitute for y, we have this right here. So really, we can substitute and say that cost is equal to 17x plus 8, 350 over x. And to be honest, you could find the derivative and then find the minimum of the derivative. But that is such a waste because this is a because this is a calculator question. And you could really just graph this and find the minimum, and that's all you need. And so if you graph this and you find wherever the minimum is, and you find the output, y, whatever the value for the output is at the most minimum value of the graph is actually your cost. If I did this right now, as I will actually do, we will get an answer. Now, conventionally, if this wasn't a paper 2, then you'd have to do the first derivative. You'd have to do the first derivative testing to actually determine if it's a minimum. Then you'd have to plug in your x value for the minimum back into the original function in order to get a minimum cost. But fortunately, this is not a paper 1. This is a paper 2. What I got was $436. Boom. Oh, so in the expansion of the derivative f prime of x, so this is calculus, the coefficient of the term in x. So here's what they're doing with you. They're getting you to do calculus, and then they're also getting you to do a bit of binomial expansion. So that's a double whammy, but we know how to do this. This is just the chain rule, and the chain rule tells us that, like an onion peel, we work from the outside in. And if we consolidate, like, I wouldn't call it consolidate, if we just multiply 5 and 2x together, this is what we get. And we are interested in the x5 term. So we already have an x out here, which means we're interested in finding the x4 term, which will multiply with the x itself to yield the x5 term. And so what we actually have is 10x. In order to get a power of 4, we need to find the power of 4 in here. But it's already this is already raised to the 2. So in theory, we need the term that when multiplied with the 2 will give us 4. And very simply, that is actually just 4 choose 2. And I'll show you why. Because then the inner term here is x2, but we're going to raise that to the 2, and this multiplies to 4, and 4 times 1 right here gives us 5. And then we also have a to the 2. And of course, we're going to set that equal to 960 x to the 5, because that is what holds. And just off the top of my head, 4 choose 2 is 6. You can plug that into a calculator if you don't believe me. So we get 60x, x4, but 1 plus 4 is just 5. So we can actually consolidate that right on the spot. A squared equals 960 x5. However, we're just interested in looking at our coefficients, so these bad boys can go away. Now we can just really work with what we need here is 60a squared equals 960, and from the top of my head, is 960 divided by 60 is just 16. A is equal to the principal negative square root of 16, which is just plus or minus 4. 7-mark question, we crushed that in not even 7 minutes. See, this is the thing. IB gives you so much time. You really shouldn't be stressing too much over it. And honestly, these questions are very easy if you can just kind of understand what they're trying to get you to do. So this other question here is one about leopards. We have an exponential function, endangered snow leopards. Quick idea here is throwing in some biology. If you take biology, you'll know what I mean, but this is actually just it's definitely a predator-prey relationship. The hare and the lynx, is that what that is? I think this is the most common example of a predator-prey relationship, where when one goes up, one population goes up, the other goes down, and vice versa. Anyways, enough with biology. Let's see what's going on here. So after 1 year, it's estimated that this is true, and we have this. Now, what they're trying to get you to do is they're trying to really get you to rearrange this function. So let us do that. Pt over P0 is equal to EKT, but it's distinctively after 1 year. So we can just say P1 over P0 is equal to EK, and T of 1 is just 1, so I'm not even going to bother. But we can make the substitution that this fraction is actually just 0.93 is equal to EK, and if we take the natural logarithm of both sides, we get that ln 0.93 is equal to K, which if I plug that into my calculator, is actually just negative 0.0726. Now, interpret the meaning of the value of K. I'm not going to write this down, but K is essentially the rate of change of your snow leopard population. And given the fact it's negative, there's an exponential decrease in the rate at which the population of leopards is changing. So you can just remember that. So this one is a GDC question, and it's because we have an inequality. And I mean, I guess you can do it just with a calculator, but you'd save a lot more time just graphing the function. So you can graph, what you'd like to graph first is, well, first of all, remember that PT over PO is just really EKT by our manipulation. And we know what K is. K is just this, so you can plug that bad boy in. I'm going to plug in ln of 0.93 because that is the exact value. And we're going to set that as less than 0.50. Essentially, what this means is if you graph the two functions, you want to find the nearest whole number where the function, this, is less than the value, this. So it's the number whereby this function is actually below the 0.50 line, but at any such x value, or I guess t value, where we have a whole number. So this is when I calculated it, 9.55, but this is not a whole number, so we shift that to 10. And the reason we shift up is because if we shift down to 9, we're still greater than the cutoff 0.50. So always make sure you're reading the question. For me, the value I got was 10. All right. A garden bed has a large number of flowers. Surprising. The height of the flowers are normally distributed with a mean of 43 centimeters and a standard deviation of 6 centimeters. Right away, this is setting us up for normal distribution. A flower is classified as tall if it is taller than 48 centimeters. A flower is selected at random. Find the probability that this flower is tall. So the inequality, or the probability they're trying to find, is actually distributed normally. And it's this right here. So we're going to go to our distribution function, second function, VARS. We're going to normal CDF. Our lower bound is going to be 48. Our upper bound is going to be 10 to the 99. Our mean is going to be 43, and our standard deviation is going to be 6. And we're going to plug this in. We get 0.202. Now, given that the flower is tall, find the probability it is taller than 55 centimeters. This is conditional probability. Probability of given that it's tall. So when it's given, that means that's the second condition. And if it's the second condition, it comes after. So taller than 55 centimeters, taller 55, given that it is tall. And so this is just the probability of tall over the probability of 55 cm. Actually, it's the probability that it's both taller than 48 cm and taller than 55 cm, but really that's all just saying that it's taller than 55 cm, because if you're taller than 55 cm, you're also taller than 48 cm. And if you do the quick math here, we know that p tall is just 0.202. And if we calculate what px is equal to, p probability of x being greater than 55, we can do that really quick. We go to normal, we go to our lower bound being 55, our upper bound being 10 to the 99, and we get 0.0228. And if we calculate that real quickly, as I will do, you find that it should be 0.0228 divided by 0.202. I get 0.112. Two flowers are selected at random. Find the probability that they are both tall. This looks like a binomial one to me. So we have two trials. Our probability of being tall is a 0.202. And we're interested in finding it for x is equal to 2. And if you plug that in real quick, binomial PDF, 0.202, you will find that your answer is 0.0408. Okay, so 500 flowers are selected at random. Find the probability that at least 100 of these are tall. And so what I'm going to do is I'm going to do a binomial CDF situation where I'm going to say P of x is equal to 500. So this calculates, or I'm going to say P is, I don't know how to say this in math. math terms, but this is what I'm going to do. Because CDF is only, it calculates from 0 up until your upper bound, this alone isn't going to do it. So you have to do this, and then subtract from that P0 x less 99, because it's also inclusive. So this is what you're effectively punching into your calculator. And under the CDF option, you're going to do that. So your upper bound in this first one is 500. Your median is, your mean, sorry, is 43. Your standard deviation is 6. Paste, and then you're going to do that again. Subtract, except your upper bound is now 99 for the second subtraction. And the answer I got was 0.562. Cool. Using the formula, we're going to find the expected number of tall flowers. We know that that's just NP. And we know we have how many? We have 500, and we know the probability of being tall, once again, is 0.202. And that will yield us 101 tall flowers. Okay. The following diagram shows a circular crop field. Center O, radius 400. Yeah. Points AB, angle AOB. Okay. Find the length of chord AB. This is just cosine law. AB is equal to, remember, 400 squared plus A plus B squared minus 2AB, which is both our radius, which is the same, cos of 1.6 rad. And if we plug this in, I'm just going to do it all in one step because I am cool like that. So 400 squared plus 400 squared minus 2 times 400 times 400 times cos 1.6. 574 meters is what I got. Next question here. Find the area of the triangle AOB. So we know the area of triangle is just A, 1/2 AB sine C, which is just 1/2 400 sine of our angle, which is opposites to what we know here, sine 1.6 rad, and we get 0.5 times 400 squared. Sine 1.6. We get 79965, but we round to 80,000 because IB doesn't want that many sig figs. Okay. The angle BOC is 2.5 radians. 2.5 radians. Find the length of the minor arc AC. Well, to find that, we need to know what this is. This is just 2 pi minus the angles we know. And if we plug that in to our calculator, this is just 2.18 rad. And if we find the length, our length of the minor arc is just equal to our radius times theta, and that is just 2.18 times our radius, 400. We get 873 meters. Find the area of the shaded region. Well, the area of the shaded region is just the area of this sector. The area of this sector plus the area of the triangle. We know what the area of the triangle is. We don't know what the area of the sector is. The area of the sector is just 1/2 r squared theta. And we know our theta for this, at least for the arc, is, for the sector is 2.18, and we're going to add that to what we found in B, which is 80K. And if we do that, we get, at least for me, I got 2,54400. Now, the shaded region is to be planted with corn. Corn seeds are sold in bags which cost $1.40 each, so one bag is enough to... So all we need to do is, we know this is our total area. We know one bag covers this much, and this gives us the amount of bags we'll use, and this gives us the price per bag. And if you do that, 254,000 divided by 8960, and then times 140, 3969. That's what I got. It's 3969. Awesome. Last question. Whew. A particle P moves along a straight line so that its velocity after t seconds is given by this function between these in this domain. The initial displacement of P is 2 meters. Alrighty. Find the displacement of P from 0 after 4 seconds. Cool. So our displacement, well, we start 2 meters away, so that's initially what we need to add. And then in order to find displacement, it is just the integral of our velocity within the bounds 0 and 4 of our function v of t with respect to t, which is right here. I am going to plug that into my calculator right now. So you should too, because I don't expect you doing this by hand. It's going to take you a very long time. You should not do it. So I'm just plugging and chugging. Plugging and chugging, as I like to do on my spare time. And I get 5.52 meters. Cool. Find the second time for t when the particle is at rest. The particle is at rest whenever v of t is set to zero, because if your velocity is 0, you ain't moving, son. The first time it occurs is here, but we're interested in the second time, which is here. So we're going to whip out the calculator function. We're going to whip out the function, and we're going to graph this bad boy. So I'm doing that right now. And I am going to find this second x-intercept. And so let's see what I get here. What do I get? I get 3.38 seconds. Write down the number of times P changes directions. P changes directions whenever we go from a negative velocity to a positive one, or a positive one to a negative one. And that only happens twice because we only have 2 roots, so 2. Find the number of times P is neither accelerating or decelerating. This is when the rate of change of our graph of v of t is 0, or in other words, when we have any sort of stationary point, which if we count, we have, let me clear this up. We have 1, 2, 3, 4, 5, 6. We have 6. All right, find the maximum distance of P from O during the time 0 here. Okay, this is asking for distance, and this is or I guess displacement. But if you think about it, when are we going to be furthest away from O? So of course we're going to start 2 away. That's always the default, at least by this question. But we need to ask ourselves, if we go here, when does it start to detract? Well, it starts to detract after this, and that's when we start to go backwards. But if we go backwards, we're deducing from our maximum. So indeed, our maximum is all the points, all the x points where we don't begin to detract. And so that happens from here to here, because after this point here, we're starting to subtract from a value. We're going backwards. So we only want the points where we're going forwards. And so, we want to start from 0, of course, because, yeah. So this is what we got. This is our maximum. And so it's really just 2 plus 0 to our second root, which we calculated to be, at least for me, when I calculated the graph, I got 3.38, and that is what we got in our time. We start from 0 seconds to 3.38 seconds of v of t with respect to t, and if I plug that in, hold up. I get 6.47 meters. Alrighty. Well, that's that for today. And of course, if you have any questions, please feel free to ask. And yeah, peace out.